So in this video, I'm continuing my discussion on the different layers of a transformer, and today we are talking about the very final part, which is concerned with how to sample the final word. So eventually we will have a probability distribution over the different words in our vocabulary, and we'll be discussing how to generate this probability distribution and how to sample from it. So just a brief recall. Initially we had an input, which is, for simplicity, just 3 words, and we're looking at the next word prediction problem. We passed it through tokenization, embeddings, and positional encodings. Eventually this input was then transferred to a transformer block, and this is what we discussed in the previous video, this whole pipeline. And the transformer block is repeated several number of times, and eventually the output is then fed into a linear layer, and the output from the linear layer is then converted into probabilities using a softmax function. Right, so the probability distribution is then sampled for the next word, and if everything goes well, you'll have a reasonable sampling strategy which will provide you with an output that sounds reasonable. Okay, and in this case, animal is a reasonable output to have. So this is the entire pipeline, and we will in the current video we will be discussing about this part. So starting from the linear layer, I will be covering the softmax function, the probability distribution we are concerned with, and the different sampling strategies. Now when it comes to sampling strategies, I'll be discussing the most common ones. So let's first discuss about what kind of probability distribution are we actually talking about, and this makes it easier to understand the reason why we have a linear layer in the first place. So let's look into the probability distribution we are concerned with. So here's an example of a vocabulary, and this is what we will limit ourselves to. I mean, this is a very simple example. Usually we'll have hundreds of thousands of words. In the end, we also have an unknown token. So if anything is not in our vocabulary, we will put it into the unknown token. And the same behavior we would expect from the model as well. So if the model is confused, if the model doesn't know whether any of these words fit into the next word prediction, it would output unknown token. And I'm introducing a new variable n here. This denotes the number of words in the vocabulary. And now let's talk about the probability distribution that we would expect the model to output. So here is the probability distribution for the next word, given that the input is cat. The distribution corresponding to this might look something like this. So we would expect that the word would have a high probability as being the next word. All the other words don't really fit into our language structure, so all these other words in the vocabulary would have smaller probabilities. Then the next part would be the probability distribution for the next word given the sequence cat is. So initially we only had the word cat, as you can see here. Now we have added is to it. So here we would expect that the probability would be high for the word and for all the other words the probability would be low. And the same we do for the word an. Right, so the word an, when we append that to cat is, then we'll have a distribution over the next word. In this case, the probability for the word animal should be the max. So this is this final distribution is what we are concerned with, right? So this is the distribution from which we will be sampling our next word, because the input from the user is cat is an, and we're looking for the next word prediction. However, the model would still output these two probability distributions. So these two probability distributions will also be available to us. But the question is why, right? If you're only sampling this last distribution, why do we have these two additional distributions at hand? And the reason for that is the length of the sequence could change. It's possible that cat was the input from the user, and in that case you would have sampled from this distribution. It's possible that cat was an input, and in that case you would have sampled from this distribution. So because the length of the input sequence can change, the model outputs all the different possible solutions till that input sequence. So this is what is being summarized here. For the next word prediction, we only care about the distribution corresponding to the last word that we have in the sequence. So now let's look at the linear layer, and what role does the linear layer play in controlling the size of the output. So remember, this was our pipeline before we approached the linear layer. So we had the transformer block, and the output from the transformer block was denoted with H. The output had m number of rows, where m is the number of letters in our input. In this case, m would be equal to 3, and the number of columns were d. Right? So D was the dimension of our embedding space, and this was also the internal dimension of our model. This matrix now doesn't have the same dimension as what we expect from the probability distribution. So let's go back to what we discussed just in the last slide. Corresponding to the word cat, we would have a distribution over all the words given that the input is cat. Now, because the number of words are n, the number of entries for the different probabilities would be n. Therefore, for the word cat, we have n different values for the probability. Same is for the word cat is. So cat is would also result in a probability distribution over the different words we have in the vocabulary. Again, we have n number of words, and we do the same m times, in this case 3 times. So the output we are expecting from the model, which is a probability distribution, is of size n, is of size m cross n. But the output we have from the transformer block is of size m cross t. So there is a mismatch in terms of the number of columns we have. And this is where the linear layer comes in. So the linear layer would help us in 2 ways. First of all, it would correct this dimension. So it would bring everything into the correct dimension of the probability distribution that we're expecting from the model. And secondly, it would let the model discover a richer representation of this output from the transformer block if needed. Okay, so we would allow the model the flexibility to discover a more complex representation in case needed. So the linear layer is very easy. You just take a matrix W, which is of size D cross N, and you multiply this matrix from the right to the output from the transformer. So the output from the transformer is H, as we discussed earlier, and this is of size M cross D. And when you multiply it by a matrix which is of size D cross N, the result is the output, which is of size M cross N. So M cross N is actually the size we were looking for, and now we have the correct size. Moreover, this W has trainable parameters, so the model can transform the output accordingly if needed. So this weight matrix then should remind you of the way we computed the value vectors and the query and the key vectors earlier when we discussed self-attention. It has the same flavor to it. It's just that now the dimensions change. So we are moving from the model dimension, which was D, to the vocabulary dimension, which is N. So once we have this output, the question is how to create probabilities out of this output. And here we will be relying on Softmax. And I think Softmax is something that we discussed earlier. This was the key component to our self-attention layer, but I will recall this again. So Softmax works as follows. So the output which we had from the linear layer contains m rows. Each row corresponds to the different words we had in our input sequence, and it has n columns which correspond to different words in our vocabulary. Now, if you were to plot the different components of the vector OCat. Okay, so this is the first word in this vector, which is how the word cat interacts with the first word in the vocabulary, which was AB. Then the second word and the second entry corresponds to the interaction between the word cat and the second word in the vocabulary, which was an, and so on. Right, so if you were to plot these values, these vector components, you will realize that they don't need to be positive. They can also be negative, as is shown here, right? So cat an is negative, which indicates that an is not a very likely word to come after cat. And same with cat, which is negative, and denoting that cat is very unlikely to come after the word cat. But cat is a likely sequence, and that's why you have a high value for this particular entry. So there are 2 takeaways. Firstly, the values can be negative because, I mean, it was a linear layer. We didn't constrain the values in any way. So they could be negative, and they don't need to sum up to 1. Right? So they, in essence, violate the 2 basic conditions for a probability mass function. So how do we convert this into probability distribution? We use a Softmax function, and I will just briefly recall after this diagram how the Softmax function actually looks like. But here is the transformation shown for the example that we had above. So all the entries now are converted into probabilities. They're all positive, first of all, as you can see from the plot. The key thing here is that the relative ordering of the elements does not change. What I mean is that the entry cat had the highest magnitude in the output vector, thus indicating that cat is a likely sequence. So this had the highest magnitude. The second highest magnitude was for cat animal. So the same ordering persists when we apply Softmax. So even after the application of Softmax and converting into probabilities, the relative ordering does not change. And this is very crucial because if the relative ordering was changing, this would mean that in our operation to convert these vector values into probabilities, we changed the ordering of the sequence, which were important, right? So if cat animal now has more probability than cat is, that would be highly undesirable because the model is telling us that cat is has a higher importance than cat animal. Now, how the Softmax function looks like, you must have seen this several times in the past. So what you have is firstly you exponentiate each of these entries. So you take an exponential for this entry, you apply an exponential function to this one, exponential function to this one, and so on, and each of these entries get an exponential. So this results in values being non-negative because exponential function is a non-negative function. And then to make sure that all the values sum up to 1, you divide by the sum of all the values. So it's so the denominator is basically a normalization constant. And from this expression, you can also understand why the relative ordering of the entries in the vector O do not change. This is because exponential function is a strictly increasing function. When you apply a strictly increasing function, you do not change the relative ordering of the entries in the output vector. So once we have these probabilities, the question is how do we sample them? We will be focusing on a few of these sampling strategies, which are all quite straightforward and easy to understand. And I will start with something called the greedy approach. So the greedy approach works as follows. What you have is a probability distribution, as we talked about. So the distribution is over the next word. Given the sequence cat is an, this is the distribution we are sampling from. And animal, the word animal has the highest probability of occurrence. So greedy sampling just chooses this particular word, and that's how it works, right? So the next word would be animal in this case. Which also has the highest probability, and in the example that we chose, this word is also reasonable. Now this process has a few benefits. First of all, it's entirely deterministic. Okay, so the probability distribution that you have does not change, and so the token that has the maximum probability remains the same irrespective of what random seed you choose or how many iterations you run. And because it's deterministic, it's very useful for debugging. So if you have an implementation of a large language model, or you're using large language model for certain application, then debugging can be difficult if you have randomness in your sampling strategy. But with the greedy strategy, this randomness is totally removed. So debugging becomes easier. But as you might expect, this usually leads to very dull outputs, right? Because you're choosing the maximum all the time, and because of that, there is no creativity left in the system. The system is not exploring any randomness which is resulting from this distribution. So the outputs are usually dull. And secondly, it's not, and sometimes not very clear why you should just focus on the token that has the maximum probability. So consider this example. Just for the sake of argument, assume that kite had a probability which was lower than the probability for animal, but was not that small. In this case, the greedy algorithm will totally ignore the word kite whatsoever. So the word kite will not be chosen by the greedy algorithm at all, and that's undesirable because you would like to have scenarios where the word kite is also chosen, so that there is richness in your output and so on. So this feature is quite undesirable. The next approach is the simple multinomial approach. So what you do is you treat this distribution as a multinomial distribution, and you just sample from this. So when you do that, there is a non-zero probability that each of these words get selected. So animal will be selected with the highest probability, that's clear, but you might also end up with an, you might end up with ab, you might end up with cat as the next word, and so on. So the benefits of this approach are two. Firstly, you introduce some diversity in your output. So unlike the greedy approach, which was only focusing on the token that had the maximum probability, this particular approach is introducing some diversity. Sometimes you might explore other words like kite or dog or is, etc. And secondly, and this results in the output being creative. That's what I've summarized here. So the output would be creative because you're exploring more diversity. The issue with this approach is that since all the tokens have a non-zero probability of being chosen, you can get responses which don't make much sense. So here, take an example here. So let's say this is your input, cat is an. You plug this into your model, you do a multinomial sampling, and then the output is cat is an kite. because kite has a non-zero probability here, and it can be chosen with some likelihood. So you ended up with an output which makes no sense semantically, and so you do end up in these scenarios where the output is just junk words. Now we can fix this problem by trying to get rid of words which have very small probabilities, right? So if I could somehow remove words like kite or dog, which have a non-zero probability, but these probabilities are not big enough, I should be able to get more reasonable outputs. And this is what the other approaches try to do. Okay, so the first approach that we will discuss is called the top K strategy. And this is very straightforward. What you do is you say, okay, I have the following distribution, and now I will just pick the top three words which have the highest probability. In our case, the three words are cat, animal, and an. Then you just limit yourself to this distribution. So you forget about all the other words in the vocabulary. Obviously, you need to, since you're limiting yourselves to only these three words, you need to renormalize the distribution. But after you've renormalized it, you do multinomial sampling, and then you have the desired output. So there are a few benefits now. Firstly, the output is still creative because you're exploring the randomness that results from the probability distribution. And secondly, you removed all the junk words. There is one drawback though, that you're not adapting your top K set with the distribution. So even if I change this distribution, even if I were to introduce some thick tails and so on to the distribution, my set of these top three words wouldn't change. You can look at the following example, which exaggerates this problem even more. So let's say you had a distribution where all the words in the vocabulary had very similar probabilities. Okay, so not necessarily equal, but very similar. In this case, this top K methodology would narrowly focus on the top K words and would just ignore all the others, which doesn't make sense for such a distribution because since the probabilities, all the other probabilities were also similar, we should at least give some chance to other words. So that's a drawback. We don't have any adaptivity whatsoever. So now let's talk about an approach that adapts to the distribution that we have, and this is called the top P approach. And so in the top P approach, we have a threshold. Let's call it P, and for the sake of discussion, let's have the threshold set at 0.8. So what we do is as follows. So first you take the output probability distribution, and then you check, okay, which token has the maximum probability. In this case, it's animal, and how much probability is there? 0.6. Now 0.6 is lower than 0.8, so you keep on adding new tokens, and then you go to the token that has the second highest probability. In this case, it's an. So you add it to your probability sum. Now the sum is 0.81, which is greater than the threshold of 0.8. So then an and animal becomes the set from which you do multinomial sampling. So the goal is to have a threshold P, and this was 0.8 in our case, and to construct the smallest possible set such that the probability mass, or the sum of all the probabilities, is greater than this threshold. And this is exactly what we did with the word animal and an. So once you have these two words, you can just renormalize the probabilities again and do multinomial sampling from these two words. Renormalization is required because we ignored all the other words, so you still need to correct for the probability masses. They should sum up to 1. So the benefits are the same as what we discussed earlier. You have diversity in the output. You're exploiting the randomness in the output distribution. So you will have diversity. Your output will be creative. But the biggest benefit as compared to the top K approach is that now you're adapting to the distribution. So because you're taking sums of these probabilities, you keep on adding elements or tokens from which you will be sampling till your threshold is not reached. So let's go back to the example that we had earlier, right? So this example was the one we cooked up in the previous slide. You have words which have very similar probabilities, and in this case we said, okay, top K will only focus on the top K elements. If K was 2, then we will only have 2 elements in our set. Now because the probabilities are almost similar, top P will behave differently. So top P will keep on adding new tokens to your set from which you will be sampling till the threshold is not reached. Now because the probabilities are similar and the sum needs to be 1, the probabilities will be on the lower side. So you will keep on adding more and more tokens to your set till the threshold is reached. So the top P set would at least in some sense acknowledge that that we need a bigger set for this example, and that's how it adapts to the distribution that we have, rather than sticking to a limited set of top k elements. So now the last thing I want to discuss about when it comes to sampling strategies is something called temperature scaling. And temperature scaling, in a nutshell, it allows the user to make to play around with the probability distribution. So the probability distribution can be made either sharper or smoother using the temperature parameter. Now, if you remember the softmax function from our previous slides, so we had these exponentials in the numerator with a normalization factor as a denominator. So what temperature scaling does is that it introduces a new parameter t in the softmax operation. So this t then scales the different vector entries. You can kind of already infer what happens as the value of t changes. So if t is equal to 1, then nothing changes, right? So if t is equal to 1, we just recover what we had initially. That's the original softmax. But if t is smaller than 1, then if you have a large value here, then that large value will only grow larger. So it means when t is smaller than 1, you make the distribution sharper. Okay, so in this case, the probability for animal was large. This means O cat animal was large, and because t is smaller than 1, this increased the value of O cat animal further. This indeed resulted in a higher probability for animal in this case, and all the other probabilities then reduce in response because the sum needs to be 1. And obviously, if you use a t less than 1, then you result in outputs which have lower diversity, because now you have a sharper distribution. So no matter which strategy you use to sample from this distribution, you will always end up with you would mostly end up with the word animal, and that's why you won't have a lot of creative diversity in your outputs. The reverse of this happens if t is greater than 1. So when t is greater than 1, then you smoothen out the distribution. So the probability mass for animal reduces, and in response, the probability mass for other words increases. Okay, so if you were to sample from this distribution, you would have greater diversity in your output, and this obviously then increases the creativity of your writing. So the temperature scaling approach can be combined with any of the different sampling strategies which I discussed earlier. So the only key element is you first change the distribution with this parameter t. So to wrap up this discussion, I want to touch upon the autoregressive nature of transformer models, and this is something that I didn't really discuss in the previous 3 videos. So what we had initially was an input catazan, and we were looking at the next word prediction problem, and we passed it through an LLM. And this LLM would result in an output, let's say cat is an animal. So what you do in an autoregressive setup is you take this output now and you plug this back into the LLM, and this is how all the latest large language models generate text, right? So this output is now used as an input, and then this becomes a new input to the model, shown here in blue, right? So the next word could then be it in this case, and once you have this output, then you continue plugging this back into your model and generating even longer sentences. So this is how you can keep on generating content. And what would happen eventually is that the sequence length is so long that you need to truncate some information. So what models will usually do is either they will just drop off the information in the beginning, or they might try to summarize that information and pass that into the future sequences. But that's a topic of some future discussion. I won't be looking into the details of that in this video. But this concept here is nice to remember, because you're generating on a word level, on a token level. So for every input, you only generate the next token, and then to generate longer text, you take that output, you plug that back into the model as a new input, and then you generate the next token. So all these tokens, right? So we started with cat is an. So all these tokens from animal to lives, these were generated one by one, and that's crucial to remember. The generation doesn't happen all at once in one go. So with that, I wrap up the discussion around transformer architecture. In the next videos, I'll be discussing more about certain specific technologies when it comes to large language modeling.